The addition rule for probability. Probability of A, you can write the word and there. The probability of A and B, sorry, I wrote it wrong. That's the U looking thing, my goodness. A or B, this is the and symbol. Here's the addition rule. If you wanted to figure out what's the probability of A or B, we can really see this and understand this well if we think about a Venn diagram. In blue, I've got my circle for A. In black, I have my circle for B. And let's see, I sometimes have designed, I'm going to design a pen specifically to help you understand this. Let's go this thickness and that transparency. Perfect. So probability of A and B. According to the formula, it says add the probability of A. So I'm going to color this in with this beautiful new semi-transparent mauve pen that I've just created. There's a probability of A. Now, continuing with my semi-transparent mauve pen, stump, special, we'll have to add semi-transparent unicorn, because it's kind of like shaped like a unicorn horn, mauve pen, my stump. There we go. Continue with my stump. When I draw probability of B and something happens in the middle, can you see that the middle is a little bit darker? If I were to change the transparency a little bit different, maybe it would show up even more. But this middle section, when I color all of A and all of B, the middle section gets colored twice. What is this middle section? Make it even darker. That middle section, oh wow. That middle section is A and B. So when we do the probability of A plus the probability of B, we've counted the middle section twice. And you can really see it when I colored it in, that that middle section got darker because it got colored twice. And so when we want to figure out the probability of A or B, which means you're going to count this section, and this section, if you count all of A and all of B, you would have counted the middle twice. So you need to subtract it. And that's the addition rule, or the formula for probability of A or B. Okay? A card is drawn at random from an ordinary pack of 52 playing cards. Find the probability that the card is a heart or a king. Most of you would probably just start to figure this out logically. How many hearts are there? 13. And we have to count the kings as well. But I've already counted one king in my 13, then I still have 3 more kings to go, so you'd probably logically just count it out to be 16. Okay? But the probability formula for OR, the addition of 2 things, we could have figured out the probability of hearts or kings and written it out. What's the probability of getting a heart? What's the probability of getting a king? And then how many are hearts and kings? 13 out of the 52 are hearts. 4 out of the 52 are kings. We have to subtract the king of hearts because we counted it twice. And we get 16 out of 52. There's 13 in this circle, 4 in this circle, 1 in the middle, there's going to be 16 cards that are hearts or kings. Now in this case, it was pretty easy to do it just logically, right? But if I gave you a question that said spades or an even number, right? So you could get a 2, 4, 6, 8, or 10, 5 even numbers. I think it would be easier to say, okay, I have 13 spades. There is 5 even numbers times 4 different suits, minus the 5 that I've already counted. Or maybe you would logically just think about 13 spades and then 5 even numbers from the remaining 3 suits. That would work as well, to count it. So you toss 1 6-sided dice. Probability that it's larger than 3 or even. Larger than 3, I'm going to circle in green. Even, I'm going to circle in red. Okay? Again, in this situation, I would probably expect you to just write out the answer by thinking about it. What's the probability of getting larger than 3 or even? 4 out of the 6. Okay? Does it matter that the green and red circled some twice? No, unless you're using the formula. Right? If we want to use the formula and write it out properly, probability, I'm going to describe greater than 3. Here's your or symbol. I used a big E for even. You could write out the word even if you liked as well to make it even clearer. Here's my formula. How many are greater than 3? 3 out of 6. How many are even? Those are the red circled ones. 3 out of 6. How many were both? 2 out of 6. What do we get? 4 out of 6. Would I probably just recommend logic on this one? Probably. But there are times where you have to have an understanding of a formula to figure it out. Oops. And these are the questions the IB likes to use. I call them non-contextual formula questions, because they just give you symbols, and from those symbols you have to figure out a bunch of other symbols. So there's no storyline here. There's no real life example. It's just a question of, do you know your formulas and can you manipulate them? So what do they tell us? Probability of A is 9 out of 20. Probability of B is 3 out of 10. The probability of A or B happens to be 2 times the probability of A and B. What's the probability of A or B? Okay. There we go. Here's our formula for probability of A or B. It's the probability of A plus the probability of B minus the probability of A and B. We can do some substitutions from what they're given us. We know probability of A and we know the probability of B. If I subbed in those two things at this point right here, right? If I put numbers in for those two, this equation still has two things that I don't know, and both of those things are different. Do you remember systems of equations? When you have two equations with two things that you don't know? This is one of the most, like, you need to know this from grade 10 and grade 11 is when you did systems of equations. You need to know your systems of equations, but on an IB exam, they will never ask you a systems of equations question right from the beginning. But it will always be a tool that you need to use somewhere inside of a question. In this case, I have two things I don't know in this first line. But I can solve for that by substituting in that I know probability of A or B is equal to 2 times the probability of A and B. And now that second line is an equation with just one unknown. Right? I can combine my like terms, add another probability of A and B to this side to get 3 of them. Add my fractions together. And solve that the probability of A and B is 5 out of 20. Once I get the probability of A and B to be 5 out of 20, I can now work back to that original formula to find the probability of A or B, which is 1/2. We now have also enough information that we could represent this as a Venn diagram. Everything's out of 20, so you imagine having 20 people, right? Event A is people who like albatrosses. Event B is people who like baboons. Okay? 5 people like both albatrosses and baboons. We have, because the baboon total probability is 9, or is 3 out of 10, which is 6 out of 20, there would be one person that likes only baboons, anti-albatross. Right? And there's 4 people that would like only albatrosses. They walk around with ban baboon signs. And there would be 10 that really don't like either of these animals due to traumatic childhood experiences. Okay. So now that we've drawn out a Venn diagram, parts B and C can be easier to figure out. In fact, we can figure them out directly from our Venn diagram. What is the probability of not, that little dash mark is the complement, not A and B? How many people are in A and B? 5. How many are not in A and B then? 15. So part B you can figure out directly as being 15 out of 20 from your Venn diagram without having to use any formulas. What's the probability of A and not B? Again, we have to take out, I have to bring out my stump pen. Here we go, we got to design it again. I had it a little bit thicker, and transparency, we'll go transparency about there this time. If I want to figure out A and not B, well, what's A? That's the blue circle. What's not B? anything outside of B. Okay? So if I'm looking for A and not B, it would have to be in both of those. Can you see what got shaded double? You guys all have to go out and buy a stump so you can do these questions. It's the 4. So part C, from our Venn diagram, it's easy to see that it's going to be 4 out of 20. Okay, did I use formulas here? Oh, that's a good formula to use. So I solved it first with Venn diagrams. How could you use formulas to do these? Not A and B would be 1 minus the probability of A and B. And we figured out the probability of A and B to be 5 out of 20 earlier, so you get 15 out of 20. Part C, that one I guess I just did with the Venn diagram. I'd like you to try example 4, another non-contextual one. Check how you did. Plug in your probabilities using your formula. And you would get 35% for the probability of B. Then the probability of not B would be 65%. Or, if you didn't want to use your formulas, you could draw your Venn diagrams A and B. If you know the probability of A and B is 0.2, you could put that in to start. The probability of A is 0.55, so that would tell you this has to be 0.35 for those to add up. A or B is 0.7, so all 3 of these have to add up to 0.7, making this 0.15. If all 3 of these add up to 0.7, that makes this 0.3. What is everything outside of B? So if you color in everything outside of B, you have the section that's 0.3 and the section that's 0.35 colored in. That adds up to 0.65. So here you have a choice. You could go with your formula work and find the probability of B, or you could draw a Venn diagram and figure out what sections are not in B, everything outside of the green circle, and find out that that adds up to 0.65 as well. If you have to answer a bunch of questions, usually the Venn diagram is the best, because you can get a lot of information from it quickly and easily. Sometimes you have to go to your formulas. Did I fix the typo on yours? No. Okay, so you have to fix this. This is probability of A and B equals 0. Technically, it would be the same anyways. If the intersection is 0, that means that the two circles don't overlap. It makes sense to draw the two circles separate in your Venn diagram. We call this mutually exclusive, when there's no elements in common. Right? A zoo has 15 albatrosses and 10 baboons. It has no animals that are both albatrosses and baboons at the same time. There are no, what would those be called? Albaboons? Maybe? I can't do it the other way. Boy, that's hard on my head. If you start with baboon and end with albatross. Baboomatros? Yes, okay. Yes, these are animals that do not exist. They cannot happen at the same time. And so you have your two circles separate. When you have mutually exclusive events, the addition formula stays the same, but you don't need the last little part. The last little part is this part, right? Probability of A and B gets subtracted, but since this is equal to 0, we don't need to write it. That being said, I actually would want you to just memorize the original formula, which has the minus probability of A and B, and then you're like, oh, that's 0 in this case. It's not actually worthwhile memorizing two separate formulas. But it does simplify, because that probability of A and B is 0, so now you can just say probability of A and probability of B. If you have a zoo with 100 animals, 50 of them are albatrosses, 49 are baboons. It's quite the zoo. One other animal, which we don't know what it is, right? You pick an animal at random, what's the probability it's an albatross or a baboon? Well, you have 50 plus 49, 99 out of the 100 would be one of those two animals. Right? So lots of situations where we have mutually exclusive. You have a class of 30 students. 20 are named Albert. 5 are named Betty. None of them are named Albert and Betty at the same time. Quite rare. Oh, there. Now you've got it. You've got the name of your first child. Something you want, something unique. Pretty sure there's no Albert Bettys out there. That could be the name that you go forward from now on. Albert Betty. People would ask, is one of those a middle name? Nope, that's my whole first name. Beautiful. So card is drawn at random from an ordinary pack of 52 playing cards. Find the probability that the card is an ace or a king. This is really easy because you can't have both at the same time. They are mutually exclusive. There's 4 aces, 4 kings. 8 out of 52. You could use the formula if you really wanted to. Probability of an ace or king, 4 out of 52 plus 4 out of 52 minus 0 out of 52 would still give you 8 out of 52.